In our last section of the semester, 14.9, we're going to continue on with our discussion of minimum and maximum values. In this section, we're going to look at optimization problems. These are similar to our problems from single variable calculus. Remember, with an optimization problem, you have a function, but you also have a constraint. And we're going to use this constraint to help us find our minimum and our maximum values. In three-dimensional space, this is what it looks like. So let's look at this diagram here. Let's say we have this nice curve. And here the curves in this section are going to be nice closed curves. So if there are mins and max, we can find them. So this curve in the xy plane is called our constraint curve. So maybe our surface doesn't have a min or a max. However, if I take my constraint curve, it's going to correspond to a curve on my surface, which is nice and closed, and it will have minimum and maximum values. So the curve on our surface is what we call our objective function. And when we find our minimum and maximum values is with respect to this objective function. It may be easier to see if we look at a specific example. In this example, we have an elliptic paraboloid. We have the equation for this particular elliptic paraboloid. Now notice that this actually doesn't have a max value because it grows forever and ever and ever. But let's just say that we just consider this curve in the xy plane, which we call our constraint curve. That's going to correspond to some curve on our surface that will have a min-max value because it's a nice closed curve. The way we find it is by using gradient vectors. Going back to a previous section, remember that when we were finding maximum or minimum rate of change or growth rate, that occurred at the gradient vectors. So all we have to do is find gradient vectors where the level curves of my elliptic paraboloid, so we're going to be looking at the second diagram here, it's going to be where the level curves intersect our constraint curves so that the gradient vectors are parallel. So notice at this point P, negative square root of 2, positive square root of 2, it intersects a level curve of our function f and our constraint curve. So this point is on the constraint curve and the level curve. For both of those curves, the gradient vector, remember that's normal, and not sure the length of these guys, but what I do know is those two gradient vectors are going to be parallel. Now they could go in different directions, right? That doesn't matter as long as the gradient vectors are parallel. Because if they are parallel, then they're going to differ by a constant, and they also indicate where we have min's max. So since they differ by a constant, and the constant we're going to use is down here in these notes. So if our gradient vectors are parallel, they differ by a constant. We're going to call that constant lambda. So that's the Greek letter lambda. That's our Lagrange multiplier. So the Lagrange multiplier is just a constant so that the gradient vectors are equal. This idea may be easier to see in this last diagram. There's a close-up of that point P. Notice that I have my level curve, I have my tangent vector, and then I have, for G, I have my normal or gradient vector, and then on the level curve F, at this point, we also have a gradient vector. They're both parallel. So the strategy is to use my constraint to find our min and max by finding our gradient vectors, setting them equal to each other. This box at the bottom just formally describes what we talked about. So we have our function that's differentiable. Let's say that we have our constraint curve, which we call G. If f does have local extreme values, so mins and max, then they're going to occur where the gradient vectors are equal, or parallel, sorry. So that means they're going to differ by some constant lambda. Now here we are assuming that the gradient of g is not equal to 0. So that's a bunch of words. Let's see how we find these min and max values. Well, the first thing we want to do is we want to compute our gradient vectors. And then we look at 1. Find values of x, y, and lambda. If they exist, they may not exist. Remember, we're solving an equation. Sometimes there's no solution that satisfy these equations. Set the gradient vectors equal to each other with some lambda, and then set your constraint curve equal to 0. You actually don't have to set it equal to 0. And then 2. You're going to find points x and y when you solve this equation. All you have to do is plug it into your function f. Largest value is your max, and the smallest value is your min. Example 1, we want to find the minimum and maximum values of our function f, which is x plus 2y. It's subject to this constraint x squared plus y squared is equal to 4. So this would be our constraint g. First thing I want to do is I want to compute my gradient vector for f and g. The gradient of f is partial with respect to x, so that would be 1. Partial with respect to y is 2. The gradient of g, partial with respect to x, and now if you set this equal to 0, that's what we're finding the gradient vector for. But the 4 will just go away, it's just a constant. So in this particular constraint function, it's not necessary to set it equal to 0. But to be safe, you can always set them equal to 0 when you're finding the gradient. It becomes 2x, 2y. So remember that these gradient vectors will correspond to local mins and max as long as the gradient vectors are parallel. So that means that my gradient vector at f is going to be equal to lambda times the gradient of g. If I simply set these vectors equal to each other times some lambda, then I can go ahead and set up my equations. Remember, they have to be equal component-wise, so that means 1 is equal to lambda times 2x, or 2 lambda x. 2 is equal to 2 lambda y. So unfortunately, I have 2 equations but 3 variables, so I can't solve. But remember the points, the x and y that we're trying to find are on our constraint function. So I also have the function, or the equation x squared plus y squared equal to 4. And it doesn't matter if it's set equal to 0 or not. Remember, the goal here is just to solve for lambda, x, and y. Now 3 equations, 3 variables. Algebraically, I should be able to solve if there is a solution. So how you proceed at this point is up to you. One thing you can notice is that if you take the first equation and you solve it for x to get 1 over 2 lambda equal to x. Second equation, solve for y, you'll get 1 over lambda after you reduce. Then you could put those x and y values into the constraint. What that will give us, it will give us one equation with one variable. So we're going to have 1 over 2 lambda squared plus 1 over lambda squared, my lambda is starting to look like an x, equal to 4. So I can solve this for lambda. Once I find lambda, I'll plug it back into the first 2 equations to figure out the x and y. And that's the goal, to figure out the points x and y on G that will be our critical points, and they may correspond to mins and max on F. Solving, I get 1 over 4 lambda squared plus 1 over lambda squared equal to 4. 5 over 4 lambda squared equal to 4. it looks like I'm going to have lambda squared equal to 5 over 16. Our lambda is going to be equal to plus or minus square root of 5 over 4. So I found my lambdas. I am now going to plug those values into my x and my y, so that my x value, let me write down which lambda I'm using. So let's say that I'm looking at lambda, oops, too big. Let's say I'm looking at lambda equal to the positive square root of 5 over 4. Then that's going to correspond to an x value of 2 over the square root of 5 and a y value of 4 square root of 5, and no need to rationalize. So that point, 2 square root of 5, 4 square root of 5, that point is a critical point. If lambda is equal to the negative square root of 5 over 4, then that corresponds to an x value that's negative 2 square root of 5, y value of negative 4 square root of 5, corresponds to this critical point 2, negative 2 over the square root of 5, negative 4 over the square root of 5. So again, these are my critical points. Something to note is these critical points are on G. So you may want to plug these points back into your function G just to make sure you did your algebra correctly. So if you do put these in for your x and your y value, you'll find that they work out, their points on G. So we found our possible critical, or our critical points, and we have to find possible min and max. Now all we have to do is take these points and plug them into our function f. So we're going to compute f of 2 over the square root of 5 and 4 over the square root of 5. I get 2 over the square root of 5 plus 8 over the square root of 5. My pen is dying, so 10 over the square root of 5. I would probably rationalize this, because if I do multiply top and bottom by square root of 5, I get a really nice value. I get 2 times the square root of 5. If I put in negative 2 over the square root of 5, negative 4 over the square root of 5, that's going to correspond to a negative 10 over the square root of 5, or negative 2 times the square root of 5. So the largest value, in this case I only had 2 critical points. So the largest value would be my max, so that would be the 2 times the square root of 5. Smallest value will correspond to a min. And that's the basic idea with all these problems. It's all algebra based. And notice that there are other techniques you could have done as well. You didn't have to solve it that way. You could have, I just want to go over algebra because I know sometimes we forget. You could have noticed that when you got your equations with your lambdas in them, you could have actually solved this for the 2 lambda, because that's common in both equations. So you could have gotten that 2 lambda is equal to 1 over x, and 2 lambda is equal to 2 over y. So if 2 lambda is equal to 1 over x and 2 lambda is equal to 2 over y, you get 1 over x is equal to 2 over y. The problem is you lost your lambda, but it's still possible because it's 1 over x equal to 2 lambda equal to 2 over 5. Algebraically, once you get rid of that lambda, the question becomes, what happens if lambda is equal to 0? So this is true provided that lambda is not equal to 0, because if lambda is equal to 0, then we have 1 over x is equal to 0, 2 over y is equal to 0, which can never happen with those particular equations. So you got to be real careful with your algebra. Make sure that everything makes sense. However, let's say you did this, and then we took this equation 1 over x equal to 2 over y, which actually gives us y equal to 2x. We can plug that into our constraint. So we have x squared plus the y squared is going to be 2x squared equal to 4. And then solve that for x. We'll get corresponding y values for these x values, and that will give us our critical point. Going back to lambda not equal to 0, you still have to check to make sure that if lambda is equal to 0, do we get a solution in that case? And in that case we don't, because if we do put 0 in for lambda, it doesn't work in our equations. I'm not going to finish. So we looked at two possible methods for solving algebraically. Let's look at another method. I want to kind of cover as many common methods as I can so that you have a lot of options when solving. Some methods are better than others, especially if your equations are really complicated. In example 2, we have a function subject to means this equation is our equation G, our constraint equation. First thing, compute your gradients. The gradient of f is 2x, 2y. Gradient of G is equal to 4x plus 3y, comma 3x plus 4y. And now these are going to differ by some constant lambda. That will give me these two equations, 2x equal to lambda, and I'm going to keep this in parentheses, the 4x plus 3y, and 2y equal to lambda in parentheses 3x plus 4y. Now remember, I can also use my constraint equation, which is 2x squared plus 3xy plus 2y squared equal to 7. I don't have to set that equal to 0. Now I'm going to do a different technique than I did previously, sort of similar to that second method. What I notice with these two first equations is that I have a 2x and a 2y. Well, it would be really nice if this was a 2xy and a 2xy for both, because then I can set the right-hand sides equal to each other. So I'm just going to take my first equation and multiply both sides by y to get 2xy equal to lambda times y, parentheses 4x plus 3y. And then the second equation, multiply through by x to get 2xy equal to lambda x, parentheses 3x plus 4y. Now this might not be the most efficient way to solve this, but again, I just wanted to cover another technique. At this point, since they have the common 2xy, it must be true that lambda y, parentheses 4x plus 3y, is equal to lambda x, 3x plus 4y. And now I have to be really careful that my x's and my lambdas don't look alike. What I'm going to do now is I'm going to go ahead and get rid of the parentheses and see what this looks like. So I have 4 lambda xy plus 3 lambda y squared is equal to 3 lambda x squared plus 4 lambda xy. At the previous step, I know that some people might want to just divide by lambda on both sides. But remember, you can't do that. You're not supposed to divide out by a variable because you don't know if that variable is 0, and we're not allowed to divide by 0. So you got to keep it there. However, we are allowed to subtract and add quantities from both sides, because regardless if our variables are equal to 0 or not, subtracting or adding 0 does not make a difference in your equations. So I do notice that I have a 4 lambda xy on both sides of this equation that I can subtract from both sides, which gives me 3 lambda y squared, 3 lambda x squared. And again, I don't want to divide out by lambda because I don't know if lambda is 0. But I can divide by 3 because 3 is not 0. We get down to lambda y squared is equal to lambda x squared. So the way we solve this algebraically is we set it equal to 0, we set each factor equal to 0. Again, I don't want to get rid of my lambda because lambda equal to 0 is a solution to this equation, and I'll lose that solution. So setting this equal to 0 by subtracting the lambda x squared from both sides, I can see that common factor of lambda can be factored out. And then within the parentheses, I see that I have a difference of squares, which factors as y plus x times y minus x. Now that I have this equation set equal to 0 and it's all factored, the only way this equation can be true is if each factor is equal to 0. And I know this is so minor, this algebra, but oftentimes we get up into the higher levels of calculus and we forget all these algebraic properties. So we have lambda is equal to 0, y is equal to negative x, and y is equal to x. Well, I need to find ordered pairs x and y. I need to find my critical points. So what I'm going to do is I'm going to look at each one of these values. I'm going to start out with lambda equal to 0. I'm going to plug that lambda in to the equation where I first use my lambda, which would be the 2x equal to lambda times parentheses 4x plus 3y, and then the 2y equal to lambda times parentheses 3x plus 4y. If I plug in 0 for lambda, I'm going to have 2x is equal to 0, and I'll have 2y is equal to 0. So x is equal to 0, y is equal to 0, and then I have this critical point 0, 0. Remember, this critical point has to be on our constraint function. So is this on G? Actually, it's not. If you put in 0 for x and 0 for y, you get 0 is equal to 7, which is not true. So when lambda is equal to 0, it corresponds to the point 0, 0. That's not a point on our constraint function, which means I cannot use this value for a critical point. Let's go to y equal to negative x. Okay. Again, there's infinitely many solutions, so we can plug in this y values. Why don't we use the constraint equation? If we put in negative x for y, then we'll have one equation with one variable. And in fact, it's going to be 2x squared minus 3x squared, I think, plus 2x squared equal to 7. Yeah, that looks correct. Combining like terms, I get to x squared is equal to 7, which means x is equal to plus or minus the square root of 7. We have critical points. Remember, y is equal to negative x. So if x is equal to the positive square root of 7, then the y value is going to be the negative square root of 7. And then the negative square root of 7 for an x value gives you a positive square root of 7 for the y value. So these are our critical points, provided these points are on G. Are these points on G? If you put in the square root of 7, negative square root of 7, it works, and they both work. Let's try y equal to x. So if y is equal to x, again I'm going to put the x, I'm going to substitute x for y in my constraint to get 2x squared plus 3x squared plus 2x squared equal to 7, or 7x squared equal to 7. So my x squared equal to 1 gives me x equal to plus or minus 1. My possible critical points, since y is equal to x, would be 1, 1, negative 1, negative 1. Okay, so again, these are my possible critical points. Are these on G? If you plug in 1, 1, negative 1, negative 1, they work out, so they're on G. So yes, yes. So now that we got 4 critical points, we can plug them in. If we compute f of square root of 7 comma negative square root of 7, remember we're putting into those x values and y values into our function f, and our x is squared and our y is squared. So in fact it doesn't matter whether we have a negative or a positive square root of 7. These two critical values are going to give me the same z value. And when I plug in those values, I get 14. If I put in the point 1, 1, or the point negative 1, negative 1, they will give me the same value because, again, I'm squaring my x and squaring my y. And when I put those values in, I get 2. So the largest value of 14 would be my max. The smallest value of 2 would be my min. We can also use this idea of Lagrange multipliers for functions of 3 variables, but it's just going to get a lot larger, our equations. We have more equations, more variables, more algebra. So again, provided that the gradient vector of our constraint function is not equal to 0, then we would, 1, set the gradients equal to each other. They will differ by a lambda. If necessary, set your constraint equation equal to 0 so you can identify the correct gradient. 2, find all points x, y, and z. Check to make sure that they're on your constraint function, and then plug them into our function to find our maximum and minimum values. So the process is the same, it's just algebraically it's going to be a lot more difficult. Example 3, we have a function subject to, so we have our g, our constraint function. First thing, find your gradient vector. It should be yz, xz, xy, excuse me, and then the gradient of g is 2x, 4y, 8z. They're going to differ by a lambda, which gives me yz equal to 2 lambda x, xz equal to 4 lambda y, and xy equal to 8 lambda z. Again, we can use our constraint function as well. X squared plus 2y squared plus 4z squared equal to 9. Now I have 4 variables, 4 equations. I should be able to solve this. I'm going to use the previous technique, noticing that yz, xz, and xy would all be equal to each other if they were all xyz. So in the first equation, I'm going to multiply both sides by x to get xyz. Now remember, this is not the only way to solve. I'll end up with 2 lambda, forgot my 2 lambda of x squared. And then xyz gives me 4 lambda y squared. xyz gives me 8 lambda z squared. Now I can set all of these equal to each other to get 2 lambda x squared equal to 4 lambda y squared equal to 8 lambda z squared. I could reduce this by dividing everything by 2 to get lambda x squared, 2 lambda y squared, 4 lambda z squared, which is really nice. Now, again, I can factor out the lambda, set it all equal to 0, factor out the lambda, and then kind of deal with the other. Let me show you what I mean. So I could set it all equal to 0, factor out the lambda. I'll end up with x squared minus 2y squared minus 4z squared, and it would all be equal to 0. So I would have lambda equal to 0, or when I set all of that equal to 0, I just end up with x squared equal to 2y squared equal to 4z squared, which is what I had here without the lambda. So your shortcut is you could just pull the lambda out, but remember you have to check what happens when lambda is equal to 0. So I'm actually not dividing out by lambda, I'm not getting rid of my lambda, I still have to check to see what happens when lambda is equal to 0. So I'll do that first. What if lambda is equal to 0? Well, think about what that means. We're saying that the gradient of f is equal to lambda times the gradient of g. So if lambda is equal to 0, that means the gradient of f is the 0 vector. Going back to the very beginning when we were talking about properties of vectors, what that means is my function is constant. However, when I look at my function, x times y times z, that's not a constant function. It's not f equal to some constant number, okay? F is not a constant function. Which means that lambda is not equal to 0. That we can't use that one. So let's look at the x squared equal to 2y squared equal to 4z squared. That's our other possibility. And this is really nice because in my constraint equation, I can simply substitute in x squared for the 2y squared and x squared for the 4z squared. That would give me the equation x squared plus x squared plus x squared equal to 9, or 3x squared is equal to 9. X squared is equal to 3. X is equal to plus or minus the square root of 3. Plugging those x values into, again, I'm going to be using this equation. The x squared equal to 2y squared equal to 4z squared. If I plug in negative or positive square root of 3 for the x, I'm squaring it, so it's just positive 3. That would give me that 2y squared. Oh, I don't want to have it in red. That's going to irritate me. That gives me well, it helps if I change the color. 2y squared is equal to 3, y squared is equal to 3/2, which means that y is equal to plus or minus the square root of 3 over 2. And then we could do that for the 4z squared as well. 4z squared is equal to x squared, which is 3, regardless of whether it's a negative square root of 3 or a positive square root of 3. So z squared is equal to 3 over 4. Z is equal to plus or minus the square root of 3 over 2. So our possible critical points, and I'm not going to write them separately because there's just too many cases, would be plus or minus the square root of 3, comma, plus or minus the square root of 3/2, plus or minus the square root of 3 over 2. And this is an ordered triplet, x, y, z. Are these points on our constraint function g? Yes. Check them regardless of negative or positive because the x, y, and z are all being squared. So you can just try the positive one and it'll work for all of them. And you'll get 9. So all of these points are on g. If I plug in these points into my function, now I do have to be careful with negative and positives here because my function is x times y times z. So let's say that I have the positives. And I plug that into my function. That gives me 3 times the square root of 3 over 2 times the square root of 2, which is 3, I think I'm going to rationalize, square root of 6 over 4. So that's where I'm putting in all positives. So x times y times z is positive. For x, y, z to be negative, only one of these needs to be negative. So I'm just going to let the square root of 3 be negatives. I'm going to let the other two values be positive. So that gives me a negative x, y, z, which gives me a negative 3 square root of 6 over 4. So any other combination of negative, positive will either give me a positive xyz or a negative xyz. So we only get the positive 3 square root of 6 over 4 or the negative square root of 3 square root of 6 over 4. So the positive corresponds to a max and the negative corresponds to a min. Let's now apply this to an actual optimization problem. In example 4, we want to find the minimum distance between this point and our cone. So since we're minimizing the distance, this is going to be our objective function. Right? It's the function in which we want to find our min. So that must mean that the cone is our constraint. So that would be our g. So we're trying to find the minimum distance from the given point to the cone. Notice that my equation g has variables on both sides. So in this particular case, I do have to set this equal to 0 so that when I do compute the gradient, I get the correct gradient. Since I'm finding some point on my cone, I need to define that point so I can use it to write equations. So I'm just going to call that some xyz. So let xyz be on our cone. So my objective function is the distance function. It'll be the distance from xyz to my point 1, 2, 0, which will simply be x minus 1 squared using our distance formula, plus y minus 2 squared, plus z minus 0 squared, or just z squared. I need to compute the gradients, but I do not want to compute the gradient for that distance function because it has a square root. However, if I square both sides, it's not going to change the points where I have a min or a max. So I'm actually going to choose to use this function without the square root. X minus 1 squared plus y minus 2 squared plus z squared. I'm going to compute my gradients. The gradient of f is going to be 2, and I'm going to leave the x minus 1 in parentheses. 2 parentheses y minus 2. 2, that's not a z, that's a 2 times z. The gradient of g is simply 2x, 2y, and here we have the negative 2z as we set that g function equal to 0. And differing by a lambda gives me the equation 2 times x minus 1 equal to 2 lambda x. 2 times y minus 2 is equal to 2 lambda y, and 2z equal to negative 2 lambda z. And we also have our constraint function as well. Maybe I'll write it down. X squared plus y squared equal to z squared, and it doesn't matter if it's equal to 0 or not. I only need this function so that I can solve for my x, y, z. It looks like I can divide out the first 3 equations by 2, simplify it further. X minus 1 equal to lambda times x, y minus 2 equal lambda y, and then z is equal to negative lambda times z. So again, I have a variety of techniques that I can use. When I'm looking at z equal to negative lambda z, that seems the easiest one for me to solve for. I'm just going to simply set this equal to 0 to get z plus lambda z equal to 0. Factor out my z. Now that this is factored, the possibilities are z is equal to 0 or 1 plus lambda is equal to 0. So I'm just going to write lambda equal to negative 1. Let's see what happens if z is equal to 0. If z is equal to 0, then in my constraint function, I will have x squared plus y squared is equal to 0. This can only be true if x is 0 and y is equal to 0. So my point 0, 0, 0 may be a critical point. Is this point on G? And it is. So this would be a critical point. Let's look at what happens when lambda is equal to negative 1. When lambda is equal to negative 1, I'm going to go back to these equations, x minus 1, y minus 2, and the z equation as well, to figure out what x, y, z goes together when lambda is equal to negative 1. In the first equation, I'm going to have x minus 1 equal to negative x. So solving for x, I get 2x equal to 1, or x is equal to 1/2. The other equation with the y becomes y minus 2 equal to negative y, so 2y equal to 2, y is equal to 1. And my z value, if lambda is negative 1, just becomes z equal to z, which I don't really have a solution for because all real numbers will work. So I need a specific z value. What I'm going to do is I'm going to take my x and my y value and I'm going to put it into my constraint function. So once I put it into my constraint function, I'll have z squared is equal to 1/4 plus 1 Solving, z squared is equal to 5/4, so z is equal to plus or minus the square root of 5 over 2. I have my possible critical points of 1/2, 1, and then the z value can either be the positive or the negative square root of 5 over 2. If I put these points into my constraint, they work, so these are critical points as well. I have 3 critical points. I need to test them to see if they correspond to a min or a max. What I'm putting them in is my distance function, not f. I only used f so that my computations would be simpler. But I'm minimizing the distance. So the distance at the critical point 0, 0, 0 gives me the square root of 1 plus 4 plus 0, so the square root of 5. The distance at the point 1/2, 1, and I'll use the positive square root of 5 over 2. Also notice that if I put in the negative square root of 5 over 2 into my distance function, since I'm squaring z, it'll give me the same value. So I just have to check this one. It looks like that would be 1/4 plus 1 plus 5 over 4. So the square root of 10 over 4, or the square root of 10 over 2. So the square root of 10 over 2 is smaller than the square root of 5, which means the square root of 10 over 2 is our minimum distance. So going back to what we were supposed to find, we were supposed to find the minimum distance. Notice that this minimum distance actually happens at 2 points on the cone. 1/2, 1 positive square root 5 over 2, and 1/2, 1 negative square root 5 over 2. However, we weren't asked to find the point that corresponds to the minimum distance. All we were asked to find was the minimum distance. So this is just one application of how we could solve an optimization problem in three-dimensional space. That's it for this section, and that's actually it for the material of this course.